today we're having another change of pace in our class. We are going to start talking about mechanical things. So if you remember, we started the class talking about terminology. That's like the practice of welding. What are things called? Then we talked about metallurgy, right? And we learned so much about metallurgy. There's so much more to learn, but you can put a pretty good fight now with what you know about metallurgy. And then we made a new tack, and we started to talk about the physics of welding and about the plasmas and the ionization potential and arc stabilizing elements. And then we put all that together, and we started to talk about real engineering. When we put it all together, we could talk about voltages and powers. And for quiz 4, right after this lecture, you'll be able to calculate deposition rates. You'll be able to calculate the things that relate to efficiency. You'll be able to calculate things like thickness of the heat affected zone or solidification time. The power you have now is incredible. So from learning the practice to metallurgy to physics to some sort of mechanical engineering, now we're going to get into the realm of civil engineering. We're going to see what in the end matters. Does the weld break or doesn't it? Is it strong or not? And we're going to look at 3 topics. One is one that is a topic in which we talk about, is about judgment. That is what I'll discuss first. Then we'll learn to calculate what size should a weld be to carry a load and a purpose you mean. And then third, we'll talk about residual stresses and distortions, for which we have made amazing progress in our lab based on all this understanding we've been building so far. So let's start with the part that is more about judgment, for which we have no formulas, but is going to help us think, and we'll never see a weld the same way again. Much of the slides that follow are slides that were prepared by Dr. Dwayne Miller, who's an adjunct professor associated with the Canadian Center for Welding and Joining. And he has come twice to Edmonton to teach his course, and he was very, very, very generous in sharing with us his material and letting us use it in our class. So we're very fortunate for that. Also, some of the material comes from Dr. Gilbert Grandin, who used to teach at U of A too in civil engineering. So let's get started. So, reference material. These slides will be uploaded as soon as we finish the class. They are already uploaded. They just didn't have this reference material that refers you to the Lincoln Procedure Handbook. So let's talk about design of weldments. So an interesting thing about the design of welding is that we spend relatively little money in designing, but by the end, something is done. The consequences of that design had a very big impact on costs. So these numbers, 5% of design, of cost is in design, and 70% is, that influences 70% of manufacturing. That's what I heard from Dr. Grandin. But for sure, cost of design is low, implications of design are high. And these, without thinking, implications of mistakes. And those of you with field experience, you probably know that you spend a lot of time welding for certain money, but then you spend crazy high money in a rush to make up for the mistakes that somebody should have seen and they didn't see. And those are millions of dollars. maybe more. But you're not going to make those mistakes because you come like well prepared and thinking ahead. So Dr. Miller, he through his experience at Lincoln and the experience of his predecessors, like Dr. Omer Blodgett, who worked at Lincoln and is the one that first that got a serious compilation of this material in the form of the books, like the one you have and other ones, companion book. They came up with 12 principles of connection design. And these principles are not like mathematical taxonomy, are principles that are relate to common sense. Of these principles, I'm going to discuss the first three, but here listed to you. So the first says, determine the load, the load to design the weld. I'll get into more detail about that soon. Second, this is kind of obscure until you see what I mean. Provide a path for the force to enter into the section that lies parallel. This is not clear just in words, but we'll discuss and will open your eyes so much. The third principle is provide a member when the force changes direction. This is not intuitive at all, but after I explain it to you, you'll start looking for welds everywhere to see these things in action. There are other principles like don't put welds into bending. Right? I will not discuss that, but some of these are self-explanatory. When you put a weld into bending, tends to open at the root and crack. Something that there's no secondary members in welded construction. If you remember on our first class, when I gave an introduction to welding, I gave the example of the Alexander Keelan platform, in which they did a weld in a secondary member that didn't matter, except that it did matter because when they put a hydrophone and they had too high of a cooling rate because they didn't, the one who welded didn't know what they were doing, and because it was too hard, it cracked and broke the member, and the whole offshore platform collapsed and people died. Watch your toes. This has a big implication about fatigue. That is because the toes of a welder are the point of stress concentration. Remember your roots is more or less the same thing. The roots, for example, in the case of pipes, the roots are inside, and that can give that is what is carrying the fluid, right? And in the case of civil construction, very often the roots are a point of a stress concentration too. Nothing welds are good for nothing. That I'm not going to get into detail, but sometimes people make welds as if they didn't matter. So why would you do them? Because actually, if you do them as they don't matter, they actually end up not being good for anything. Consider manufacturability. Again, this is about judgment, but so many times you get to see people with brilliant designs that everything can always be built. But the price you would pay because of the poor design is exorbitant. And if you had thought ahead of time, the price would be so much lower with the same functionality, just because the welds are now where they should be and in a reasonable way that is accessible, that can be, the weld can be positioned, and many of those things. About welding, all right, there we go. If you check out the chat, Eddie just shared some of his own experience as a welder and as a engineer at Suncor, at Syncrude. And number 10, don't just fix the problem, look for the root of the problem. This is especially relevant for fatigue. It's very common that you can see that when you see a fatigue crack in the field, people go and grind it and weld it. And you know what? The next day, then you have now 2 cracks, 1 on each toe. What are you gonna do? Like grind it and weld it and have a 2 to the end progression of cracks? So when something goes wrong, more than just fixing it, You have to think, why did it go wrong? Because just welding what broke, very often only will is going to bring nothing but more cracking. Based on these principles we're going to be discussing, very quickly you'll start having thoughts about what to do and what not to do. Respect material properties, right? Like you cannot ask steel something that grade of steel is not meant to do. And number 12, the last one, is see what they're doing in the shop or in the field. And this is really important. The main criticism of us engineers by people in the trades is that we talk without knowing. But if you go, and I laugh at myself about talking without knowing, but it's not that true. I do talk to the welders, and if you go and talk to the welders, you'll realize one of the most interesting things of welding, that in welding, you start by knowing the answer to pretty much everything. Because if you ask the welders, they always know the answer. If you ask them why, then it gets interesting, because very often their interpretations are based with the only science they know, that sometimes is not enough. But they typically know the answer. And if you're going to be in your cubicle thinking that you're going to solve a problem just based on a book, let me tell you, it's going to take you a long time and your chances are very low. You go, you talk to the guys, great. So that's number 12. Let's start with number 1. So determine the load transfer through the connection when specifying weld details. Right? Weld details are things that are welded, right? And determine the load transfer. Let's see this in an example. For example, we have this I-beam, and we want to make this this plate for say, for example, for hooking a chain to it, hanging from it. And the question is, all right, I'm going to put some load here, so this plate should be strong enough so I don't rip it off. What size should the welds be? And when we talk about size, in the case of fillet welds, in North America, size means the leg. In Europe, size can mean the throat. For those of you who might have forgotten, the leg is what lies parallel to the, is the part of the weld that lies parallel to the members, right? This is the face of the weld, the toes of the weld, and the throat is what goes in diagonal. And we have the nominal throat, the theoretical throat, the actual throat, right? We're gonna be using always a nominal throat in these calculations. So what size, when we say the leg is, the size is, what size of leg? There are some like heuristics, like rules of thumb that say, well, your leg should be 3/4 of the thickness of the plate. And this is based on some kind of the two throats in that case would have more or less the similar strength as the base plate, roughly. That's, if you don't know what to do, that's what you do. But depends on what you're doing. Sometimes you should know what you're doing. And here we have an example. If we were to have this 1 inch thick plate, right? 3/4 would be 19 millimeters. Something else is you could say, you know, I know that if I put weight in this hole through a pin, the plate is going to shear off. And I can do some calculation of shear and realize how much load can this plate take. And then I design my welds to take that load, to be as strong as a plate. Let's say in the case we have a chain, and should we design for the strength of the pins or the strength of the shackle or the strength of the chain? I have a straight answer for this. So as I'm saying, how do I design my welds, right? I gave you many options, and all of these options are reasonable options. But I'm going to tell you which is the most reasonable option, that is what you should do, and is the principle number one. It is, we design for the load. So if we're going to have a very strong load, we put a strong weld. If we are going to have a weak load, we have a weak weld. Of course, out of practical reasons, we're never going to do a weld that is 1/4 of a millimeter, because such a thing cannot be made in practice. But in that case, we're going to see people define what is the minimum size you can make a weld. But other than that, when we design a weld, we're going to design it to bear a given load. Right? Of course, if we don't know what the load is, what we have to do is guess what the load would be. But it's not true that we would always go and design according to the thickness of the members, because sometimes the members might have a big thickness that comes for reasons that have nothing to do with bearing a load. So let me move this here. Okay, so in this case, we what we do is to use the minimum, and there are two things we want to do: to use the minimum leg size, right? Well, as small as possible, and the minimum length that I can have. Right, I start by having the minimum leg, and then for that leg, what is the minimum length? In the case in which we have bending, for example, in this case, this is an I-beam that is manufactured, right, with fillet welds. This is a case of huge I-beams. For example, Supreme Steel makes these type of beams for bridges. In countries such as Chile that are fairly remote in this southern tip of the Americas, and without a strong steel industry, actually they pretty much manufacture pretty much every I-beam, because it doesn't make sense for them to have a large stock or to wait too long to import. So I-beams are often manufactured either because they're huge or because there is no an economy of scale. How do you design these welds? What size should you give them, right? And this is very interesting. I'm not going to get into all the details of this now, but those of you who have taken strength of materials would realize that when we have bending, also we have shear. And in this case, we can calculate the shear associated with bending through the standard formulas. And we're not going to be using these formulas in class, but I'm showing you this as things to keep in mind. And we would design these welds to deal with the shear that is induced by the bending of this beam. This is an interesting one. In Japan, the anti-seismic columns tend to be these kind of closed box sections, right? So there's going to be tension or compression on these type of columns. What size should we make this beam? Can anybody make a suggestion? So the loads, this column C is tension and compression. How would I say? What size would I give to these beads? So something you can think is, what is the nominal load that these beads see under tension or compression? Anybody? Okay, so I'm going to tell you. So if we're under tension or compression, these beads that are in the line of stress, actually, they are not pulling almost pretty much any load. So in this case, these beads that are not transferring load, nobody's trying to separate one plate from the other. these plates would be using the minimum weld size, which is established in the codes, and we're going to be going over those, right? Would be silly to make these 3/4 of the thickness. That would be so expensive for no reason. All right. Principle number one, the bottom line, principle number one is we designed a weld for the load it must carry and not for other reasons. Number two, this is the one that had kind of an obscure statement. So I'm not going to restate this, but let me show you what I'm meaning by this. Let's have this I-beam. And in this I-beam, we want to put like this plate with a hole to take some weight, right? In this case, that's pretty good. You see, this plate is aligned with the web of the I-beam. So we weld it, and we put the load here, and the load gets transferred to the web of the beam. This kind of makes sense, right? And everybody's happy. This would be a good design. So let's see alternatives. How about, and in this case, the weld has the load distributed, right? So how about if I think of a different alternative? Why not put our plate with a hole like transverse, right? We said that the principle said, let's make it parallel to the sections, but in this case, it's transverse. So we put our welds. So far, it looks pretty much the same as before. It's so not the same as before, but looks the same as before. We put the load, and the load will be distributed in the web. But now, let's see what happens. The distribution of stress is very uneven. Don't do this. Can anybody suggest? I'm going to give a couple seconds. I imagine that many of you are with a mind on the quiz, but why would I have this kind of a hill of a stress distribution instead of a uniform distribution of stress? So do you realize that for a given average stress on the weld, this part here is a part that has concentrated a lot of stresses? Why? I will tell you. What happens is that this part of the weld is pulling on something very stiff. That is the flange of the weld. So this wants to pull and really has the whole flange. Yeah. The load is transferred to the web here, but here on the web. But here in the flange has compliance, right? I can, if I were strong enough and I push up and down on the flange, I would be bending the flange. Now, if I push up and down on the web, it doesn't move all that much, right? I have all this enormous section blocking me. So what happens, and this is exactly what you would see if you do finite elements, when these parts that are more compliant, they take less load. They take less load because whatever load is going here gets relieved by the bending of the flange. What is against the web? No, that is very stiff. So don't do that. But what can you do? Look at this, and this is pretty cool. If I really wanted to have my plate transverse to the web, I can do it. Then I would put these load transfer plates inside, and I would weld them to the flange, and I would weld them to the web. And now this is great because this plate is against the very rigidity of these other plates, right? So we made the sections transfer load in a parallel way. That's the way it was framed. But the way I see it myself is all about stiffness, right? So now the flange here is not compliant anymore. It's very stiff. An interesting thing, should we put a weld up here? Yes or no? Who says yes? Who says no? Thank you, Wes, for answering. But the funny thing is, the answer is no. And you know why? Because whatever load we would be transferring to the flange would be on the compliant part. So this part would be bending without giving us much strength. But in addition, there is very little load that goes up to this part, because this plate transfers the load to the flange, and if the flange wanted to bend, is actually transferring it to this other reinforcement plate. And all the load happens kind of in this little triangle here. All this other part might as well not be there. We could even do this kind of rocket ship configuration, and that would be okay, right? We are having some sort kind of a buttress transferring the load. And the load, we distributed now, the stresses, we don't have the stress concentration in the center anymore, because everything is equally stiff, right? Very, 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 very interesting. How about if we want to do something similar with the I-beam or in an horizontal shape? Now, look at this. This design is not so good, right? What do you think about this weld here? Do you think this weld here is taking a whole lot of load? This weld here is not taking a whole lot of load because it's against the web that now, because the web is horizontal, is very compliant. So this weld is not doing a big job. These two welds on the side, those are against something very stiff, right? And because now it's stiff because it's the web, the flange being vertical, they became stiff. But are these welds long enough, right? So let's not do this, right? Like the load is coming through these little parts. So that weld didn't matter. So we can take it out. But is this strong enough? What would be a possible solution for this? Solution would be a reinforcement plate. Now, if I put a reinforcement plate on the other side, all of a sudden I made this web, right? That because it's horizontal and we're pulling a transverse to the web, that used to be very compliant, now became very stiff. And now we're happy. Now this is a good weld, right? It's very interesting. The concept here so far is, let's weld on what is stiff and let's not weld on what is compliant, because what is compliant, it takes very little load, and the load can then would be distributed into the stiffer parts. And you end up with a problem of stress concentration. That means you might end up breaking part of a weld. Okay, an interesting one. Let's put a load-bearing plate on a pipe. Okay, good or bad? What do you think? Good or bad? Bad, horrible. Yeah, thank you, Eddie. If you pull here, what's going to happen? I pull the load, the part that is taking care, the stiff part of the pipe is the vertical part, right? This is not really a sharp line, but the vertical part of the pipe is the one that is stiff and is the one bearing the load. And in this case, on the side view, I would be distributing it fairly uniformly. So I wouldn't be having a stress concentration lengthwise on the weld. But right here, check out what would be happening. Check out the toes, right? What you don't want is a tension in the toe, because a toe is a stress concentration point. Ha! What do you think of that? Of course, this is exaggerated. But if I wanted to put this plate on bearing load on the pipe, I would end up with all kind of problems. If it is cyclic loading, I would end up with problems of fatigue. Remember, one of the principles was, watch your toes. There you go. This toe is opening up. And Professor Miller has lots of stories about probably welds that went wrong by having a stress concentration in the toe in this type of loading, right? Bad design, right? That would end up having a stress concentration and having a short life. I love formulas, but I cannot put this into the way of formulas. So thank God, like Professor Miller, like gave us his slides, and they are so self-explanatory. They help us think. All right. How about this? Okay. If we put the plate instead of aligned with the pipe, we put it transverse. We can put the weld there. But this is going to be another very bad idea. We put the load is resisted by the stiff part of the pipe. And here, we would have a very uneven distribution of load on the weld. Very similar story than before. The more vertical we are, the stiffer we are. The stiffer we are, the more load we take. And this part, as it starts to become more vertical, it starts to take more load. This part in the center is very compliant, takes little load. In this case of the weld, the start and the end are going to be subject to stress concentrations that maybe were not obvious when we first thought, right? We just think it's a plate on a pipe. And we don't see the pipe deform with our eyes. We don't see anything like that. We don't see this kind of light bulb shape deformation. But it is there. And the metal is very sensitive to deformations that are invisible to the eye. And that is how it cracks. And in addition, of course, we would have another problem of toe opening, which reduces fatigue life and performance. What can we do? Well, one of the things we can do is we wanted to align the members in parallel ways, right? The way I see it is we want to weld on what is stiff. And what was stiff? Well, stiff is the vertical part of the pipe. So I can put these plates here. This looks like Abraham Lincoln's beard, right? And we can weld to the stiff part, and then and then down here. And everything now is in a chain of stiffness, right? This is one possible solution. Some people might say, well, it doesn't look so pretty. And this is one of the interesting things in the design of weldments. Very often a pretty solution is pretty bad for performance. And very often, a good solution is not so good looking. And in particular, when we care about costs and about ease of manufacturing, sometimes the well-engineered solution is pretty ugly. So we have to keep this in mind. We have to keep this in mind, that beautiful is not the same as good, ugly is not the same as bad, of course. Ugly welds often mean defective welds. but things like this, in which we have the plates coming at an angle and having these cross members and having this kind of section here that is that doesn't have a plate. Sometimes it doesn't look so appealing to the eye. But when we think, there is a good purpose for this. Another possibility, if we can, and that will depend on the size of the pipe and many other factors, accessibility. If we can, we can weld a stiffener ring inside. And then, yes. Now, for example, this might be more beautiful, but this is a lot more expensive than this. Chances are that an engineer would like this one. The architect would want this one. And I don't know who pays. Maybe that's the one who is going to have a final say. But isn't this interesting, right? In this case, if we put a stiffener ring, we would be transmitting the load to the vertical parts. And watch this. This is a very interesting thing. These welds here are going to be taking a lot of load because they're going on the stiff parts. But these other welds, they're on the more compliant parts of the pipe. Do I need them? Well, I'm going to show you this other one. And here we have the stiffener ring outside. Now that gets interesting, right? In this case, that is a single plate. That would be hard to thread. Maybe we should make two halves there. But look at this. Here we have another possibility that is much the same. It's similar to this one stiffener ring that went all the way around. This one goes only up to the stiff sections. And what I was trying to mention before, all this part here that is against the compliant part, it doesn't take that much load. If we wish, we can take it out. Of course, we're going to see how we design for the size of this weld. But we should be aware, and for this, we do not have formulas. You can do finite elements, but really, do we need to? Because very often we can imagine all these things. We in this weld here, the load is distributed with an emphasis on the vertical parts connected to the stiff sections, and with very little contribution of the center. When we design a weld, very often we assume that the weld is stressed uniformly on its length. Often that's true. It's not true in this case. So this is a better solution. Shorter welds, well designed, right? Cheaper, less material. Look at this. This is a photo of that Professor Miller took, right, at an airport in the US. And I am sure I've been there, but I cannot remember which one it is. Look at these tarps here, right? And this is very designed with a lot of sense of architectural aesthetics. See how this hook attaches to the pipe. Let's make it clear, closer. What do you think? Huh? This is exactly what we were discussing. What did they do? And if you see, the weld goes if you see, the weld goes from here to here, right? It doesn't look all that clear, but I think what it is. But in any case, see how it's grabbing from the stiff parts of the weld to support this hook. That's exactly what we're talking about. Let's talk about principle number 3. Oh, no, not number 3. We have a couple more examples here. Let's look at this hollow section. Good or bad if we put this this plate here? Good or bad? Yeah. Aha, some say good, some say bad. No, this is bad. This is bad because we're welding against a compliant section, right? This horizontal part is like a membrane, right? We can put our weld there and we put load that is going to be resisted how? On the vertical sides, right? On the parallel sides of the load. And although the weld would be distributed in that direction, or we think so, when we pull, right, this is going to deform this way. We don't see it with the eye, but it does deform this way. And what is happening? We're opening the toes. We're opening the toes, and that's bad news. Never a good idea. Right? And the start and the end of the weld is also going to be stressed out. We don't want to do that. What can we do? The good old trick of the transverse plate. We weld it there, but what do you think? Is this going to be a uniform stress distribution or a non-uniform stress distribution? Uniform or not uniform? Okay. Not uniform, not uniform. What is going to be, where is the stress concentration going to be? Beginning and end or middle? What is going to be having the highest loads? The ends or the middle? The ends, absolutely. We put the load, resist on the sides, and because this part is stiffer than this part in the middle, we go with a stress concentration at the ends. What I find amazing of these slides of Professor Miller is that it helps us think. Of course, you can do this with finite elements, but doesn't mean that we should do it with finite elements. Really? Are you going to ask some kind of PhD person to do a calculation for you that we can now envision? So I love formulas, but in this case, it's not about the formulas, it's about the judgment we are developing. And in quiz 5, I'm going to be asking you things like this, good or bad? And you shouldn't be doing like solid mechanic calculations. It's by looking at these type of principles, you'd be developing your judgment. Right? And not good there. So what do you do? We do what we have discussed. We try always to attach to the sections that are the stiffest sections, right? This type of arrangement, for example, that it looks very much like the stiffener ring inside the pipe we discussed, right? And as we discussed, we don't need to weld the top because the top is very compliant. It's not going to give us much strength. And also, there's not much load that reaches the top. These two guys are taking lots of load and is transmitting it to this, and through this now very compliant member that we made very stiff with this stiffener plate, this became quite good. Now in this hollow section, we needed to have access inside, right? Sometimes we can, sometimes we cannot. There are other ways too. Imagine we cannot have access. We can do this, right? And again, like for example, I don't like seeing these gaps here. But you know one of the reasons why people leave a gap? Very often they design the gap because if they don't put the gap, the welder will want to weld it. Because when you see something that is in what you think is the path of the load, you think the load goes from here to here. But no, it doesn't. But when you see it in reality, not in this abstraction, you really feel really, really tempted to weld it. So very often they leave this big gap. So the welder that doesn't succumb to temptation, right? In this case, look, stiff plate goes through these other stiff side plates that go transfer the load straight parallel to the vertical members that are the stiff ones bearing the load. Here we have the Abraham Lincoln Beard solution, right? How about this one? And here's showing again a gap so you don't weld it. Can you weld it? Yeah, you can. Do you gain anything? No. You lose anything? Yes. You lose lots. You lose time. You lose money. You put weight. You have a chance of a defect. So the best weld, and we discussed this in the interaction, the concept of joining in our second lecture. The best join is the no join, right? The best weld is the no weld. We weld because we have to, and we love it. But if we don't have to, don't do it. Okay. I find it amazing that those things we just discussed, in which we, all of a sudden, we have built our very own internal finite element system in our head. And forever on, we're going to be looking at joints. And very quickly, you'll realize that some joints were made by designed by professionals and some by amateurs. You'll see both. You shouldn't. You should see only the professional ones. Are you guys? You're going to do only the professional ones. You're in awesome shape. Principle number 3. This is a really cool one. It talks about forces changing direction. So, for example, let's look at the structure that could be, for example, the structure of a shed, right? Then we have these beams here, and we would put a load. The cross-section here is I-beams, right? The cross-section is I-beams. Well, it's not an I-beam, it's manufactured I-beam, right? Like in this case, have not a constant section, but this is secondary, the constant section. But what matters is, let's say we put a bending moment on this corner. You might think that putting a bending moment in this type of corner arrangement is not necessarily much different than putting a bending moment on a straight I-beam. However, it's so different. And let me show you how, because this was not obvious to me at all until Professor Miller taught me. And that's what I want to pass on to you. Thanks that I had a happy life in my ignorance, but I have a so much happier life now that I've seen the light, and the light is coming to you. So here's the corner we were talking about. And so we're welding on the web, and the flanges are welded too. But there's something interesting. When we put the bending moment, that means that here at this corner, we have a force on the flange. Let's look at the flange. Let's look at the web, at the part of the web. We have a force that comes here, that at the bottom of the web, another force that comes there. And here at the top of the web, we have a force that goes out and in, right? If you have taken strength of materials, this will be quite obvious to you. If you have not, you have to use a lot of imagination. So, right, like this is a payback from those of us who knew metallurgy, and the guys who knew strength of materials were struggling with the austenite and martensite. Now, payback time. Those of us who knew martensite and austenite are thinking about strength of materials and forces, and the guys who didn't but have the strength of materials are thinking, oh, this is trivial. And for welding, we need to know everything. So at the web, what we have is that these forces balance each other, right? Like, and in the web, we are gonna see that the web is in tension, right? In this case, sorry, the web is in compression, right? These two forces put the web in compression, and the web has this force pushing out. So this is a force balance at each of these corners at the web. But let's look at the flange tip, right? Let's look at the tip of the flange. There is no web now. So we have these two forces coming in. And my question is, what balances them? How about the other one? We have the two forces coming out at the flange tip. What is balancing them? At the web, it was the web that was in compression that created the balance. But now at the flange tips, we have a load unbalance. Of course, because there is no accelerations here, somehow they balance. And you know how they balance out? Because they bend. And do you want, and then we say we shouldn't put bending on the welds, right? The flange, the edge of the flanges, in this case, this part is going to bend in, and this other top part is also going to be bending in. So the flanges are going to be crunched up inside. Not a good thing to happen. Well, you don't have that problem with bolted joints, and it's interesting because in bolted joints, you have a plate and another plate, and this plate reaches all the way to the edge of the flange and acts as a stiffener against the flanges moving in. So what do we do if we don't have a bolted joint? What we do, okay, I'll tell you what we don't do first. What we don't do this, because putting this type of stiffener on the web does nothing for my flanges. What else I don't do? I don't put like a reinforcement on the web like that. It's still compliant. Bad. You can put lots of plates parallel to each other, and it's not going to have a significant effect on the stiffness. How about this? This is on the web, right? And guess what? No, this is not going to work either, because it's on the web and the tip of the flange is still bent. Look how they do it. What they do it is you weld. This is at O'Hare in Chicago. Look at this. In this case, they welded a stiffener plate. Isn't this amazing? You know exactly why they put this plate here. And it's not obvious at all what load is being transferred. But now you know that what this plate is doing is preventing the flange from bending into inside or outside, depending on the direction of the moment. Isn't this awesome? You're going to look at welds now, and this is going to be like, oh, I know why this happens. So this is this third principle. I think it's really amazing that we get to see these things. You can do them all in finite elements. Really, we don't need to, right? And you're going to start to see how sometimes these joint details are, these weld details are well done and sometimes not well thought out. So this is from Gilbert Grandin, Dr. Grandin, right? So some things that are bad practice. To do like 100% continuous fillets or groove welds. Very often, if we don't have the loads, we try to make everything over-designed, right? But when we design things, at least with a little bit of information, especially about the loads, then we might not make huge welds, and maybe the welds are so small that we meet the minimum weld size, because we cannot make a microscopic weld, right? And if we do the minimum weld size, then we don't need to weld, is already over design. So we don't need to weld all the length, and we can do stitches, right? We already talked about stitches during terminology, right? And save time and save money and save weight and save on distortions, right? Sometimes people try to make sure it's a good weld, so they increase the fillet size, and every time you round up and the next guy rounds up and they round up and round up, you end up with huge fillets which don't have a reason to be. Now, if the fillet is too big, you're spending more money in consumables, you're spending more money in welder time, right? And in addition, if you put a big weld, your residual stresses and your distortions are going to be bigger too. So you don't want to underweld. We all agree on that. But overwelding comes at a price. And the smarter we are, and the more relevant our weld is, the more important is that we don't overweld it, and we do it just right. Design good practice. Size the welds for the load. Use fillets every time we can, because the fillet essentially is a pre-made groove. Use stitch welds when we meet the minimum fillet size, right? When we cannot make welds, we wish to make a very small weld, but the code says, no, you should never be smaller than some size. Okay, so then we go stitching. Don't oversize. Partial penetration groove welds is, we've been discussing quite a bit about fillets, but sometimes we might have a butt joint, and the butt joint is not transmitting a whole lot of load. Do I need to go full penetration? No, I don't, right? And put welds only where we need them, and we discussed how we could have overwelded, for example, stiffener plates by, for example, welding on the top. But that adds nothing and brings many potentially bad things. And the other thing is consider fatigue when necessary. We will not discuss fatigue in this class. I would love to. It's just like, I know you guys are handling a lot as it is, but for that, there are formulas, and it's an amazing field. So I will switch now from these judgment principles for weld design. I will get into formulas now to calculate the design of a fillet, the size of a fillet.